Next up, we have Yuichi Harikane from the University of Tokyo, who will be talking about UV luminosity functions.
Okay, thank you very much. Can you hear me? Yes? Okay. So, hello everyone. I am Yuichi Harikane from University of Tokyo. So, first of all, I thank organizers for organizing this very nice conference and inviting me. I will talk about very high redshift galaxies and agents observed with JWST. So this middle panel here shows the history of the universe. As you know, after the Big Bang, the first stars and first galaxy form at least 20 or 30. Then these galaxies evolved through the cosmic time, then finally became galaxy in today's universe. Then in this context, we want to understand how galaxies form and evolve in the 30.8 billion year cosmic history. For example, we want to understand when the first stars form and first galaxy form and what are their properties. And also we want to understand galaxy evolution. The galaxy evolves through the cosmic time regarding the mass evolution, size evolution, heavy element evolution. And also some people may be interested in the co-evolution between the galaxies and their supermassive black hole agents. As you know, JWST is now successfully finding many high redshift galaxies. So this figure shows the UV magnitude as a function of the redshift. And these gray points show the HST previously selected galaxies. So this red diamond shows the galaxy candidates selected with the early JWST dataset. Even with the early dataset, we found more than 20 galaxy candidates, at least beyond 9. Now there are many more JWST datasets. For example, JS GTO team are now finding more than 700 galaxy candidates from vacuum images, at least beyond 8. So based on these many findings of the high redshift galaxies, people are discussing the number density, UV luminosity function, or the star formation rate density evolution. So this figure shows the star formation rate density or the UV luminosity density as a function of the redshift. And this gray data point at least beyond 10 are the JWST observations. As you can see, this JWST observation shows higher star formation rate density than this model prediction. Here, this model is as a model assuming the constant star formation efficiency. Although this model can nicely reproduce a redshift evolution from less 0 to 10, however, at least beyond 10, these models start to underpredict the star formation rate density. So there may be a tension between the JWST observations and the model predictions. However, there is one concern about a low redshift interloper, because these observations are based on the galaxy candidates selected with the vacuum images. For example, the previously claimed redshift 16 galaxy candidate, although this was a very good candidate, I also selected this galaxy as a high redshift galaxy. However, with the NASPEC spectroscopy, it turns out to be a low redshift interloper at least 4.9, where very strong H-alpha and O3 emission lines enter the broadband and medium band photometry, and they boost the photometric fluxes, and resulting in the similar the SED similar to redshift 16 galaxy. So this kind of contamination with very strong emission line can be eliminated if we have multiple million band filters that can be tracing at the continuum level. However, this really indicates that spectroscopy is important to understand the galaxy formation in the most distant universe. So that's why we are now focusing on the spectroscopically confirmed galaxies. So this figure again shows the UV magnitude as a function of the redshift, but all of these data points are the spectroscopically confirmed galaxies. This includes the GNZ11 and the most distant galaxy at least 14. So this is an example of the spectra of the redshift 11.04 galaxy, which clearly shows the Lyman break here. And sometimes, if we are lucky, we can also detect emission lines. So far, the spectroscopic redshifts are very agree well with the photometric redshift. So this figure compares the photometric redshift as a function of the spectroscopic redshift. So except for a few examples, most of them agree well with each other. Then we calculate the number density of the spectroscopically confirmed galaxies. So these two panels show the UV luminosity function at least 10 and 12, and these red data points show the constraint from the spectroscopically confirmed galaxies. So because we are counting only the spectroscopically confirmed galaxies, so there is no concern about low redshift interlopers. So this gray data point shows the results from photometric candidates. So we found that our spec-Z constraints are consistent with photo-Z results. Then we compare with the theoretical model predictions. So at least 10, most of the models agree well with the spec-Z constraint. On the other hand, at least 12 with a relatively bright magnitude range of -20 or -21, then some of the model underpredicts the number density of such bright galaxies compared to the spectroscopic constraint from our study. Then, as you know, there are recently very exciting confirmation of the redshift 14 galaxies. So there are two redshift 14 galaxies confirmed so far, and the most distant one is very bright, minus 20.8 magnitude in rest frame UV. Then if we calculate number density, the number density of such bright galaxies is actually very high, which is about 100 times higher than most of the model predictions. So we don't know whether the number density of such bright galaxy at least 14 is really such high or not. So this could be boosted by the cosmic variance. Also, this error includes the cosmic variance. So I think to confirm this high density, we need a much more intensive spectroscopy targeting the bright galaxy candidates selected with a wider field data set. Then we calculate star formation rate density or the UV luminosity density. So here we assume the salpeter initial mass function. So then this figure shows the star formation rate density as a function of the redshift. And this red data point shows the lower limit of the star formation rate density, counting only the spectroscopically confirmed galaxies. So even with the spectroscopy, we're still finding a tension between the J-relativity observations and the model predictions. Then what makes the tension between the J-relativity observations and the model predictions? Because these models are calibrated with redshift around redshift 0 to 10 using the Hubble dataset. So this indicates that some of the galaxy formation processes may be different at redshift below 10 and redshift beyond 10. And as you know, there are many intensive discussions about what is the origin of this tension between the J-relativity observations and the model predictions. For example, because we are comparing with the model assuming the constant star formation efficiency, one natural explanation is a high star formation efficiency at redshift beyond 10. And such high star formation efficiency can be realized by, for example, feedback-free starburst or the very compact star formation. And also, some people discuss that if we go to high redshift, then because the metallicity is low and CMB temperature is high, then the initial mass function becomes more top-heavy. And such top-heavy initial mass function makes many massive stars and boosting the UV luminosity in these galaxies. Then some people discuss that the radiation-driven outflow is important too in the bright galaxy. And also some people recently, there are many interesting discussions about the bursty star formation, where we are selectively observing the galaxy in the burst phase. And some people even discuss that cosmology might be wrong. And some people discuss that Asian activity may be responsible for their brightness in rest frame UV. So regarding the bursty star formation history, we can understand the star formation history if we conduct SED fitting analysis. So we conducted SED fitting analysis for bright galaxies at 4 to 7 to 12, so whose optical emission lines are well constrained with medium band photometry or midi spectroscopy. So here I show the result. As you can see, all of the galaxies fitted here shows increasing star formation histories, where the star formation rate increased by a factor of 10 or 100 in the recent 100 mega years. So this indicates that recent starburst may be boosting the UV luminosity in these bright galaxies. Then what makes this starburst? Actually, we can also answer if we look at morphologies. So here I show two examples of the bright galaxy at 7 are taken with a different telescope. With the ground-based telescope and the Hubble Space Telescope, these galaxies are marginally resolved. However, with a very high resolution J-relativity dataset, we can well resolve this galaxy into the multiple clumps. So these galaxies are very clumpy, shows very clumpy morphologies. And we investigated 12 galaxies, 12 bright galaxies at rest 7, and we found that about 70% of the bright galaxies at rest 7 shows a very clumpy morphologies with multiple subcomponents. So this indicates that this kind of recent starburst observed in the SED fitting analysis may be triggered by recent merger events. So at rest 7, the merger-induced starburst may be responsible for the brightness of these bright galaxies. On the other hand, at rest beyond 10, I think the situation is a little bit complicated. At rest beyond 10, actually we found there are two types of the galaxies, bright galaxies. So one is the extended one, and the other one is the compact one. The extended galaxies have the effective radius in the rest frame UV is about 200 to 300 parsec, and the most distant galaxy at rest 14 is actually classified as extended galaxies. On the other hand, there are compact galaxies whose effective radius is less than 100 parsecs, and your famous GNZ11 and the very bright and compact galaxy in glass field GHZ2 actually classified as compact galaxies. Then if we plot them in the size evolution diagram, so this figure shows the effective radius as a function of the redshift. So the extended galaxies follow the size evolution extrapolated from the lower redshift universe. However, the compact galaxies shows a very small effective radius compared to the size evolution. And actually, the emission line properties are very different between these two populations. So here I show the example of the spectra. So this is a spectra of the redshift 14 galaxy confirmed so far, the most distant galaxy, which is classified as an extended galaxy. So this galaxy shows almost no strong emission line. On the other hand, this is a spectra of the compact galaxy, which is at GHZ2 at least 12. As you can see, it shows multiple strong emission lines, including carbon 4 and nitrogen 4. So you can see that these two galaxies have very different emission line properties. So then if we plot, for example, the equivalent width of the nitrogen 4 emission line as a function of the effective radius, we found this kind of tentative anti-correlation, whereas the more compact galaxies show the much stronger nitrogen 4 emission lines. So based on these results, we found that at least there are two different processes maybe responsible for the properties of these bright galaxies, at least beyond 10. For example, for extended galaxies, we think that major induced starburst may be responsible for their brightness and their extension. On the other hand, for the compact galaxies, the compact star formation, which could be realized by feedback-free starburst, may be responsible, and such compact star formation may enhance the nitrogen production in these galaxies, or the AGN activity may be responsible for their brightness. So regarding the AGN, if we go to a relatively lower redshift, then there are many more AGNs so far finding by JWST. So, for example, from our study, we found a total of 10 broadline AGNs at least 4 to 7 from NASPEC MSA dataset. So these AGNs show the broad HRF emission lines whose line width is larger than 1,000 km per second, but narrow O3 emission lines whose line width is typically less than 1,000 km per second. And we found these 10 AGNs from 200 galaxies spectroscopically confirmed so far, so the AGN fraction is about 5%. At redshift 0 with similar luminosity, the AGN fraction is only 1 to 2%, so this indicates an increasing trend of the AGN fraction towards higher redshift. Then if we calculate the number density, so these two panels show the UV luminosity function at redshift 5 and 6, and this red diamond shows the number density of our JWST detected broadline AGNs. And this blue curve is the extrapolation of the quasar luminosity function. As you can see, the number density is significantly higher than the quasar extrapolation of the quasar luminosity function. So we are now finding many more AGNs than we previously thought before JWST. And also at redshift 5, you can also find a similar, these red data points show the similar AGN, but found by different studies using JWST, and we find different number densities. And we think that this different number density may be due to the different sensitivity used in these studies. So this figure shows the AGN fraction as a function of the sensitivity for the broad HRF emission line. So we found that the AGN fraction is about 5%, and Roberto Mairino also found that a similarly high AGN fraction, and most of us are using the JWST NASPEC MSA dataset, which are very sensitive. On the other hand, Yortomasi found a relatively low AGN fraction, which is less than 1%, and also relatively lower number density. And actually, this is, I think, because they are using the Nantian Grism dataset, which is less sensitive to the JWST NASPEC MSA dataset. So also, this indicates that if we have deeper dataset, deeper spectroscopic dataset, we may find many more AGNs. Then because we detect broad HRF emission lines, we can calculate black hole mass. So this figure shows the barometric luminosity as a function of the black hole mass. So we found that black hole mass is about 10 to 6 to 10 to 8 solar mass, which is about 100 times smaller than the quasars. In the right panel, we calculate we show the black hole mass as a function of the stellar mass. So please compare this JWST data point with this black line. So this black line is a redshift 0 relation. So we are finding the JWST detected broadline AGNs have the black hole mass, which is significantly higher than the local radiation. So they could be they are having the overmassive black hole compared to the local radiation. On the other hand, recently there are many interesting discussions about whether they are really agents or not. I think this kind of discussion comes from the results that these JWST detected broadline objects are very weak in X-ray. For example, this figure shows the X-ray background measurement as a function of the energy. So this red curve is actual real measurement from unresolved X-ray background. And this black curve is estimated from the JWST detected broadline agents using the number density from our study and assuming the typical agent spectra. As you can see, the estimate from JWST is about 10 times higher than the actual resolved X-ray background measurement. So there is a tension between the JWST observations and unresolved X-ray background measurements. And recently, there are many intensive studies for the stacking or individual properties of in X-ray of these broadline objects. For example, this figure shows the result of the stacking analysis. They don't find any significant deviation in these broadline agents. So this figure shows the ratio of the barometric luminosity to the X-ray luminosity as a function of the barometric luminosity. So these JWST detected broadline objects shows very weak X-ray luminosity compared to this redshift zero relation for type 1 agents. So this indicates that these broadline objects may be special agents such as Compton thick agent or intrinsically weak in X-ray. I think Roberto will talk this more tomorrow. Then in order to understand these properties of these broadline objects, we recently conducted time variability analysis. So the black hole mass is 10 to 6 to 10 to 8 solar mass. Then if we use the local radiation, then the amplitude of time, variability time scale is about 300 days in observed frame, and the amplitude should be about 0.1 magnitude. Then, as you know, there are now multi-epoch JWST datasets whose time interval is about 500 days in observed frame, and of course, JWST is very sensitive. So this indicates if these broadline agents have the time variability similar to the local universe, then we should detect the variability in the non-term multi-epoch images. Then we conducted time variability analysis. However, we don't detect any time variability. So this is an example of the age broadline agent at rest 4 in the epoch 1 and epoch 2 and difference images, but we didn't see any significant detection in difference images. So this figure shows the variability amplitude as a function of the black hole mass, and this blue curve is a local relation, and this red arrow shows the lower limit for the broadline agents detected with JWST. So the JWST detected broadline object shows a significantly weak X-ray, significantly weak time variability compared to the local relation. So then this slide actually summarizes the properties of these JWST detected broadline objects. So if you look at the optical spectra, they look like very similar to the local type 1 agents. So they show broad H-alpha emission lines and narrow O3 emission lines. And if you use the empirical relation, then the black hole mass is about 10 to 6 to 10 to 8 solar mass, and the Eddington ratio is about 0.1 to 1. However, they don't show any detection in the X-ray, and they don't show any significant time variability. And then we propose a fourth scenario to explain the property of these JWST detected broadline objects. Here I show the scenario A, B, C, and D. And the first three scenarios are the special agents, non-standard agent scenario, and the final one is non-agent scenario. So because time variability is based on the non-term image analysis, and non-term image flux is dominated by continuum emission. So we should explain somehow the continuum emission from non-standard agent this continuum. So in the first scenario, we discussed that such kind of continuum may be dominated by the very stable, non-variable disk agent disk continuum. And in the second possibility, we discussed that this kind of continuum may be dominated by host galaxies. And in the third possibility, we discussed that continuum may be dominated by scattered agent disk continuum. In the final scenario, this is a non-standard agent scenario. But then if this is not agent, then we should explain the broad emission line by star-forming outflow. However, we detect broad emission line only in H-alpha. We didn't see any broad emission line in O3. So this indicates that metallicity of the outflow component should be very low, which is less than 1% solar. And also outflow velocity should be very high. So I don't personally think that this kind of AGN scenario can explain the property of these broadening objects. But I think in either case, this is very interesting object, and we need more observation to understand the nature of this newly found object. Okay, so this is a summary of my talk. So I show the recent result about very high redshift galaxies and AGNs. So we are now finding many large number of the galaxies at least beyond 10, which is more than theoretical model predictions. And at least 7 for bright galaxies, the merger-induced starburst may be responsible for their brightness. And at least beyond 10, there are 2 types of the galaxies, compact one and the extended one. And also there are many detections of the broad-line AGNs whose black hole mass is about 10 to 6 to 10 to 8 solar mass. However, the nature is not so clear because they are not detected in X-ray or time variability. Okay, that's it. Thank you very much.
All right. All right, thank you. That was great. That was a really nice overview of everything going on at high redshift. We have plenty of time for questions. So, questions? Oh, in the very back. Yes. Oh, and right there. Okay, and then we'll go to you.
Hi, I would like to comment on the AGN variability thing. I think that it's, in my opinion, it's still premature to call that, there's no detection of time variability, right? Because so far what you have monitored, quote unquote monitored, is just, a very small number of objects and very limited, time interval, right? So for example, the one that you showed is, about 1 to how many days in between? Is it something like about a year-ish, right?
Yeah, it's about a year.
Yeah, right. So I mean, I just wanted to comment that it's pretty. This is still uncertain whether those objects have time variability.
Yeah, thank you very much. Yeah, but I agree that we need a much long span observation to conclude that they don't show any time variability. But at least if we compare with the local radiation, because if the black hole mass is very small, if we use the empirical radiation, then the time scale should be very short compared to the much other more massive black holes. So then, this case could indicate that other variability property may be different to the empirical local agent. But I agree that we need a much longer time scale observation.
Okay, there you go.
Hi, this plot you showed a few times with the star formation rate density having tension with the standard models. I understand that. What I didn't understand was you did at one point show luminosity functions that they agreed with the models at redshifts of 10 to 12, or else the kind of mild disagreement. So I didn't understand the difference between those models.
You mean the difference between the UV luminosity density and you mean the difference in the number density and difference in the star formation rate density? Yeah, actually, this is a kind of accumulation of the many data points of the number density. So that's why the number density, there looks like a much significant excess compared to the number density.
Oh, it's past redshift of 12 when you start having trouble. I see.
Yeah, thanks. Well, great talk. I mean, very good overview. I have a question also on this part of your talk. Actually, well, one is a comment, one is a question. So one point is that, I mean, some of these models that you're comparing it to are not theoretical models. They're good empirical models, right? So just to make it clear that it's not necessarily, I mean, theoretical models, but also empirical model kind of show this. But then it's not that all theoretical models show this. So there are some theoretical models, some more recent simulations from FIRE, but also First Light and others who seem to suggest, or who essentially come much closer to the observational predictions. So I think there's something interesting there. So my question was, there seems to be some kind of observational debate about the UV luminosity function and the UV luminosity density at redshift maybe 10 to 12. So if I compare, for instance, the paper by Adams et al. With, let's say, the one by Donan et al., they seem to show a very large difference at redshift 10 to 12. So, and I wanted to ask you, as an as an observer, you know, so what is your opinion on this? I mean, do you have any opinion on, you know, what's going on with the observations?
So could you repeat the question? So you mean about difference between different studies or difference from?
All right. So the question is, so what can you tell us about the luminosity density redshift 10 to 12? If I compare, for instance, the works by Adams et al. With the works by Donan et al. So the works by Adams et al., for instance, shows or argue that it's actually falls off much steeper. It's much lower than what has been seen in the other James Webb observations.
Yes, I think the study showing the much steeper decline of the star formation rate that should be obtained is, I think, Willow et al., which is based on the Canucks data set. But I think I personally think this could be due to the cosmic variance, but I think we need a much larger study to conclude the difference, what makes the difference.
All right, that is the classic observer answer. We need more data. We always need more data. All right, let's thank Harikane again.